Hi everybody, I'm going to teach you about angled projectile motion. This follows from the lab you did with the FET. So we're going to summarize the key points there and then look at how to solve problems, basic problems, where if you're given a launch velocity and an angle, you can figure out how far away something lands. So I've reproduced the graph you should have had from the lab where I'm going to finish this, so at 90 degrees right there, so let me finish that. All right, so the idea is when you launch something, the range continually increases to a peak, and then the range gets smaller and smaller and smaller. So that's an unusual graph. You might have called that parabolic in the lab. It's actually not parabolic. It's actually a sine curve, but you don't have to know that. Okay, so summarize what we can learn about range and launch angle. There's a lot of problems we can do from that. As the angle increases, the range increases until, and hopefully in the lab you got 45 degrees. And some of you might have anticipated that the maximum range comes from 45, but it's not obvious why that should happen. And then it starts to decrease again. Okay, and then for a given range, there are two angles of approach. Okay, and these angles are complementary. So I didn't ask you about that in the lab, but here's what I'm talking about. Whoops, I spelled complementary wrong. Complementary. In other words, if I want to fire something in this graph 6 meters, I can do it at that angle, which is about 15 degrees, or I can fire it at that angle, which is about 75 degrees. And 75 and 15 add up to 90, hence they're complementary. If, on the other hand, I want something, I'm launching at the same speed, but I want to go 8 meters, then that's roughly 27, 28 degrees, or I could do it at 62, 63 degrees, where 62 and 63 give us the same range, or they're complementary. So that leads to an interesting way I can look at, another graph I can look at, where I can look at how high something goes versus how far it goes for a given launch velocity. So see if this makes sense. If I fire at something 20 degrees, it's going to start at 0 height, it's going to go up to some height, and then it's going to come down some range. Okay, I don't know what the range is, but I just know it's going to look like that. If I fire it at 70 degrees, you should have learned from the lab that 70 degrees is much more vertical, right? So here's, let's say 20 degrees looks like that. It's fairly flat. 70 degrees is fairly vertical. That's the angle. I'm not going to write this for some speed. So 70s go higher, but since 70 degrees is the complement of 20, it's got to go the same range. That's what that graph above is doing. So I would draw something like that, where this represents 70. It's going to go higher, but it's going to end up at the same spot. On the other hand, if I fire something at 30 degrees is more vertical than 20, so it's going to go higher, and 30 degrees is closer to 45 degrees. So if you try to gauge how far something is going to go, relatively speaking, the closer you are to 45, the closer you are going to a maximum. So since 30 is closer to 45 than 20 is, it's going to go higher, and it's going to go further. So that's 30. And if I fire it at 60 degrees is more vertical than 30 degrees, so it's going to go higher yet, but since 60 is a complement of 30, it's going to go the same range. So there is 60 and 30. And then if I do 50 versus 40, 50 is good, or if I do 40, it's going to go higher than 30, but further because it's closer to 45 degrees. And then if I do 50 degrees, it's going to fall between here, but go the same as that. So it's an interesting way of looking at how different angles give you different ranges and different heights. And if we want to try to understand why that is, well, let me do a crude little thing. So here is 20 degrees, and here is 70 degrees, right? So why does 20 go the same as 70? Well, let's break this down into a Vtax, okay? So when I fire something at an angle, okay, and that's what this is showing, I've got an x component and a y component. That's why we needed the vectors prior to learning projectile motion. So that velocity, some of it is horizontal and some of it is vertical. And if I contrast that with 70, notice that 70 is much less horizontal and much more vertical. And if I want to calculate them, right, that's where we use trig. So Vx, the horizontal component, is the adjacent side to that. So that I can say that Vx equals the launch velocity, the initial velocity, times cosine of the angle. And I can say Vy, this vector, which is the opposite side, so I'm going to use sine, is VI sine of the angle. And I would do the same thing over here. I'd use the same equations. And so what I want you to understand is that at 20 degrees, okay, so at 20 degrees, so our range, actually, I'm jumping ahead of myself, my bad. So how do we figure out the range? What's the equation for that? Well, let's put in our information. I'm going to do a Vtax table. Well, in a horizontal direction, right, that's x, that's the same as my initial speed times the cosine of the angle. That's what I just derived a second ago. And in the y direction, my initial speed is VI times the sine of the angle. Time, I don't know. I don't know time it takes to go forward. This is the time to go up and down. These are the same times, but I don't know either one of those values. Acceleration. Okay, so just like horizontal projectile motion, there is no acceleration in the forward direction, but we are accelerating downward at g in the vertical direction. So don't write this. If I do this, while I'm moving this way, I'm going at a constant speed, so a is 0, but while I'm going up and down, I'm always accelerating at 9.8. So it's just like horizontal free fall, or projectile motion, except that there is a vertical component to the initial velocity. That's all the difference. In terms of distance, in the x direction, that's what we're trying to find. In terms of the y direction, okay, that's our maximum height. So what we're interested in usually is what's the maximum height you go. And then the v at the top is the same as the initial speed. This is important, but the v at the top in the vertical direction is 0. So let me reiterate that. So if I draw this trajectory and I'm looking at the peak here, we're still moving that way, but we're no longer moving vertically. It's like firing something straight up. So that's where that comes from in that last bit of the Vtax table. Okay, so how do I find range? Well, a range is in this column, and I want this. So we're going to call range d, d sub x. Oh, actually, I'm going to keep it x because it's horizontal. That's going to equal my initial velocity times time plus 1/2 at squared. Well, a is 0, so I'm not going to put that term, and my vi is the same as vi cos theta, so x is equal to vi, the initial launch speed, times the cosine of the angle we launch at, times the time in the air. Now, we know that time in the air is twice the time it takes to go from bottom to top, or top to bottom. So again, if I draw this, if I want the total time in the air, I can figure out how much time it takes to get from here to here, and then double it because it's the same down. And so if I want to figure out the time it takes to get to the top, I have this information, actually I don't have y max. I know g and I know v sine theta. So I can use the equation. If I want to find an equation that relates initial speed, final speed, acceleration, and time, we have the equation VF equals VI plus AT. So if I solve that for t, I see t is equal to VF minus VI all over A. Now I can substitute in what's going on here. VF is 0 minus, what's my VI? Right here, VI sine theta, divided by what's my acceleration? Negative g. Now that's just the t to the top, right? Because to the top our VF is 0 vertically. So if I want the total time, so total, t total, is simply twice this. So that's equal to 2 times VI sine theta all over g. And the negative cancel out. That's why I did that. Here's the thing though. This tells me that the bigger the angle, the more time in the air. And that's what you saw in your lab. So if I go back ultimately to here, why is 20 give me the same as 70? It boils down to this. When you fire something at 20 degrees, you have a big Vx. In other words, more of the velocity is in the horizontal direction, whereas this one you have a small Vx. Okay, so if my range is based on my VI cos theta, cosine of a big angle is a small number. However, as we saw from this equation, the time in the air goes by the sine of the angle, meaning the bigger the angle, the more time in the air. So this has, since it's a low angle, it has a small time. This is a big angle, so it has a big time, and they balance out. So there's a crude explanation of why complementary angle gives same range. Okay, now, how does velocity change with flight? We've talked about this. Now I'm going to represent it with vectors. So if I fire something and it follows a path like this, Okay, what I want you to see is the horizontal vector is always the same thing. That means it's moving at a constant speed. Whereas the vertical vector, as it rises, gets smaller and smaller at 0 here, and then it starts rising again, just like if you're going straight up or straight down. So we can summarize that by saying, right, Vx is constant, and Vi is accelerated. In fact, we know the acceleration is negative g, and that means a is 0, okay? What is the acceleration due to flight? Well, I guess I just answered that. Ax is always 0, and ay is negative g. Okay, so if I ask you at this point, what's the horizontal velocity? It's the same as the Vi cos theta. If I ask you what's the vertical velocity, it's 0. If I ask you what's the horizontal acceleration, it's 0. If I ask you the vertical acceleration, it's negative g. So make sure you distinguish between those. So we can then do a example problem. So let's say I kick a football at a speed of 13. So I'm going to represent that speed with a 13 at an angle of 35. All right, what are the components of the velocity? So you should be able to draw those. So I would draw in and make a right angle. So there's my Vx, and there is my Vy. Now I can do SOHCAHTOA. I can say Vx is equal to the Vi times the cosine of the angle, and this is equal to the Vi times the sine of the angle. So you can put in 13 cosine of 35, and this is equal to 13 sine of 35 degrees. Make sure you're in degree mode. I'll let you calculate that out, okay? So you can plug in the numbers and then use them for the rest of it. Now, how do I find the time in the air? Well, if you look at the VTab table on the other side, I expect you to be able to redo that. You don't have to do that now, but we ended up with an equation that said the time in the air is equal to twice the initial speed times the sine of the angle divided by g. So please look back at that so you can derive that. And then the range, we derived that equation on the other side where it says the range, which I'm going to call x here, is simply Vi cos theta, right? We can use this value right there, and we can use this value right there. You don't have to recalculate it, times the time in the air. And you use the time in the air here to put it there. Then let's say we fired it at 55 degrees. How would things change? So our initial angle was 35 degrees, so I'm going to use that as contrast. So how about the vertical speed? Well, 55 is more vertical than 35, so that's going to go up. Horizontal speed is less because it's less horizontal. Time in the air. All right, remember from the lab, time in the air depends on how vertical it is. So the more vertical, more time in the air. Maximum height is also going to increase because the higher you go, or excuse me, the more vertical you fire it, the more it's going to go up. And then the range, we got to be careful. Okay, so the range is when we look at 45 degrees. Which one of those is closer to 45? This is 10 degrees away. This is 10 degrees away. Or you can see their complements. So the ranges will be the same. Okay, I know I've thrown a lot at you. If you're worried about more than anything, make sure you understand this and make sure you understand these vectors and the related velocities in that. The problem solving here, you're going to do a few, but that's not going to be a heavy emphasis because I know those can get confusing. You have to be able to, though, break things into components. Okay? So that's what we'll focus on, especially with the homework.